All right, we're going to try another input method here, another recording method to see if this works better. I wasn't very happy with the last section that we did. I was happy with the section, I just wasn't happy with the way the video turned out. But I'm not going to go back and re-record it now. So this is going to be section 4.3. I've got a bigger space to work on here. It's a piece of whiteboard. And we're going to talk about tonight how the derivatives affect the shape of the curve, what derivatives have to do with the shape of the graph of a function. So we're going to start a little differently than Stuart starts in his book. I'm going to start with just how a function can be determined to be increasing or decreasing. Increasing or decreasing. So here's what we know. We're going to start with the increasing slash decreasing test. All right, the increasing slash decreasing test. And what does this say? Well, surprisingly, it tells us a lot about a function from the first derivative. Here's what it says. It says this. It says if f prime of x is positive, if the derivative is positive, anywhere the derivative is positive, so if f prime of x is positive on some interval I, then f is increasing. Remember, increasing means the function goes up as we move to the right, increasing on that interval. Now, if the derivative being positive means the function's increasing on that interval, then of course it follows logically that if f prime of x is less than 0 on some interval I, then f is decreasing. On that interval. All right, so we can tell if a function is increasing or if a function is decreasing simply by looking at the first derivative. Now, we're not going to prove the increasing decreasing test, but we can look at a quick example. What this is going to come down to is where is the derivative exactly positive and where is the derivative negative? And the way we're going to find that is we're going to incorporate something called the sign test. You probably saw this back in pre-calc, but if you didn't see it back in pre-calc, that's okay. I will teach it to you tonight. So let's take an example into account here. We have a function f of x, which is going to be equal to 3x to the 4th minus 4x cubed minus 12x squared plus 5. Right? And we want to find where is this function increasing and where is this function decreasing. Now we could graph this with our calculator, but we don't necessarily always have a calculator. So we want to know where this function is increasing and where this function is decreasing. Now the way we're going to do that is we're going to use the increasing decreasing test. Obviously they named it pretty appropriately. So the first thing we're going to have to do is find the derivative, right? So we look for the derivative. The derivative of this is going to be 12x cubed minus 12x squared minus 24x, right? That's going to be our derivative. Now, if we factor that, right, we can remove a 12, and we can also remove an x, and we're going to be left with, here we're going to have x squared, here we're going to have just 12 into 12 is 1, so we're going to have minus x. 12 into 24, that's going to give us negative 2. And of course, that's going to factor further. That's going to be 12x times x minus 2 times x plus 1. Now, if you think this looks pretty similar to looking for critical values, well, then you paid attention to the last lesson. It is exactly the same steps we used when we were looking for critical values. In fact, we're going to do a very similar exercise to what we did when we looked for critical values. The whole purpose of finding critical values was to get us to this point right here in this next section. So what are we going to do from this point? Well, we're gonna write down our critical values. We're gonna find the critical values of our function. Now our function is a polynomial, it never fails to exist. So we can say that f prime of x equals 0 when, and it's pretty obvious, I mean the example is pretty straightforward. We get x equals 0, x equals 2, or x equals -1. So those are our critical numbers, critical values. Now, using those, and any place the derivative would fail to exist, if indeed we had that, which we do not in this example, we are now going to conduct something called the sign test. And if we utilize the sign test correctly, it's going to tell us where the function is increasing and where the function is decreasing. So you can pause the video, of course, if you haven't gotten all of this written down yet, but I'm going to have to erase due to the limited, that's a new word, due to the limited space that I have here. So let me take this, get this off here. All right, and we'll pick up from there. Now, if you remember, we had found zeros to be located at 0, 2, and -1, right? Those were our critical numbers. Our critical numbers were x equals 0, x equals 2, and x equals -1. So what do we do? How do we conduct the sign test? Well, a sign test is not the most advanced thing that we're ever going to encounter. The sign test, the way I like to do a sign test, we simply make a number line. We plot our critical numbers on the number line, making sure that we put them in the correct locations, right? -1 goes here. This is going to be x equals 0 over here, and then finally over here we get x equals 2. It's very important you put them on the number line correctly. You'd be surprised what happens if you don't. Actually, you wouldn't be very surprised. You just get the problem wrong. So after we've got the critical numbers listed here, we take on this edge over here, we list our factors of our first derivative. Now, our first derivative had factors of 12x, right? It had factors of x minus 2, and it had a factor of x plus 1. Those are the factors that we found when we found the critical numbers. So factors here, critical numbers across here. Now what are we going to do? Well, we call it the sign test for a reason. We're going to find the sign of each of these factors in each of these intervals. So how do we go about doing that? I don't know if that's bothering you, but it's bothering me, so we're going to fix that. So what are we going to do? We're going to pick any number we want in this interval. This is x equals -1, so below x equals -1, any number we want. We could use -2, we could use -10, -1 billion. It doesn't matter what we pick. So if we pick -1 billion, 12 times -1 billion is going to be negative, and that's all we care about. We're just going to write the sign right there. It's going to be a negative, so we're going to write a negative sign. -1 billion take away 2, that's still going to be negative, so we're going to write a negative sign there as well. -1 billion plus 1 is going to be negative, and so we're going to write a negative sign here. Now we could have just as easily used -2 or -6. Between -1 and 0, of course, we're going to have to pick something a little, something that we're going to have to maybe do a little bit of thinking. We're going to have to pick a fraction here, so we're going to pick -1/2, right? 12 times -1/2 is going to be -6. That's going to be negative. We'll put a negative sign there. -1/2 take away 2, that's still going to be negative, so we're going to put a negative sign there. Notice it's not particularly important as to whether or not we find the value. What we really need is just the sign. -1/2 plus 1 turns out to be positive, so we're going to put a plus here. Now, what else do we have? We have a number between 0 and 2. Between 0 and 2, the obvious choice is 1. 12 times 1 is going to be positive. We're going to put that here. 1 take away 2 is going to be negative, so we're going to put a negative there. 1 plus 1 is going to be 2. That's going to be positive. We'll put a plus there. Now we need a number bigger than 2. 10, 10's fine. A billion is fine. 10 times 12 is going to be positive. We'll put a plus there. 10 take away 2, that's also going to be positive. We'll put a plus there. 10 plus 1, that's also going to be positive. We'll put a plus there. Now, the reason we call this the sign test is because what we're interested in is just the signs of each of those factors. So what do we do now? Now we just multiply these together. Negative times negative times negative turns out to be negative. We'll put that here. Negative times positive turns out to be positive. We'll put a plus here. Positive times positive turns out to be negative. We'll put a minus here. Positive times positive turns out to be positive. We'll put a positive here. Now, in this example, it's the first example we've done, they alternate. They do not have to alternate. There's no guarantee that they're going to alternate. That's just a fast, wow, use words, Kevin. That's just what happened in this example. And so it's not necessarily going to be the case that it always turns out to alternate. So what does this lead us to be able to conclude? What can we say about our function right now? Well, because this is a negative sign, right? This is the derivative itself right here. This is f prime of x. This is actually the sign of the derivative. This is the sign of the derivative, the sign of the derivative, and the sign of the derivative. And the increasing and decreasing test, so wherever the derivative is negative, we're decreasing, and wherever the derivative is positive, we're increasing. So what can we conclude? We can conclude that f, the function f is decreasing. I'll cheat, use a down arrow for decreasing. F is decreasing on the open interval from negative infinity until we get to negative 1, union the interval from 0 all the way to 2. Right? That's where our function is decreasing. Now, f is increasing on, and that's going to be where our derivative is determined to be positive by the sign test. So f is increasing on negative 1 to 0, union 2 to positive infinity. So we have been able to determine, using the sign test, where our function is decreasing and indeed where our function is increasing. And so if asked, when is a function increasing, when is a function decreasing, this increasing decreasing test is our number one, and to be perfectly honest with you, the easiest way to determine. All right, so I'm going to go ahead and erase this, and then we'll move on to the next idea that we're going to talk about on this video. All right. So where do we go from here? Well, we've determined where our function is increasing, and we've determined where our function is decreasing. We've been able to come to the conclusion of this is where it's increasing and this is where it's decreasing. We're going to focus on our critical numbers to do that. What we're now going to do is summarize. We're going to summarize that. Remember, the goal in section 4.2 and section 4.3 is to find local mins and local maxes of functions. Local mins and local maxes. That's been our goal in section 4.2. It's still our goal here in section 4.3. And so in light of that, we're gonna now introduce something called the first derivative test. Okay, the first derivative test. Now, what does the first derivative test say? Well, first of all, the first derivative test tells us how to find local mins and local maxes. That's what the first derivative test does. So it's a very important test, and it's one that we need to make sure we understand fully. So the first derivative test says, suppose C is a critical number of a continuous function. There's our magic word, continuous again. F. All right. Now don't forget, continuous means no holes, no jumps, no vertical asymptotes. We can draw without lifting our pencil, right? That's our friend continuity from back in chapter 2. All right, so suppose C is a critical number of a continuous function F. Well, then there are three possible things that could happen here. We're going to write each of them down. It says first, if f prime, that's the derivative, changes from positive to negative at C, then F has a local maximum at C. So the first derivative test tells us if the derivative changes sign from positive to negative. Now, if we think this through, we'll draw a little sketch here. If we think this through, the derivative changes sign from positive to negative at C. So if we just draw a rather simple function, a function that goes like this. This is C, that's our critical number, because at that point the derivative is equal to 0. At that point, what can we say? Well, if we look at the slope of the tangent line, the derivative is the slope of the tangent line. If we look at the slope of the tangent line over here, the slope of the tangent line over here is positive. If we look at the slope of the tangent line over here, the slope of the tangent line is indeed negative. So our derivative has changed signs. Our derivative has changed from positive to the left of C to negative on the right of C. And as we can see from the picture, C does indeed turn out to be a local maximum. So that's the essence of the first derivative test. There are two more possibilities here, of course. That first possibility, A, says if F changes from positive to negative. B, of course, it's going to do exactly what you think it's going to do. It says if F prime changes from negative to positive at C, then F, right, if the derivative changes from positive to negative at C, then F has a local minimum at C. And if we draw a similar picture, right, if we draw a similar picture here, and we put in this picture someplace where there's a local minimum, here would be C, and we take a look, right, now why is that a critical number? Well, that's a critical number because the derivative equals 0 there. If we take a look at the slope of the tangent line on this side, the slope of the tangent line on this side is clearly negative, whereas the slope of the tangent line on this side is clearly positive. So our derivative, slope of the tangent line is the derivative. Our derivative is changed from negative to positive at C, and indeed C is a local minimum. Remember, C has to be a continuous function for the first derivative test to really give us the conclusions that we're stating down here in parts A and B. Now, what about part C? What does part C say? Well, part C says, what happens if F prime does not change signs? At C. I mean, that could be a possibility. When we, just a second ago, put our sign test up there, we had alternating signs. We had negative, then we had positive, then we had negative, and then we had positive. And I pointed out to you, they don't always alternate. And we'll do an example here in a second where they don't. And if they don't alternate, then what are we going to be able to say? Right? If the sign doesn't change, what are we going to be able to say? Well, that's what this case addresses. And it says, if F prime does not change sign at C, so it's positive on both sides, it's negative on both sides, then F has no local max or min at C. Then F has no local max or min at C. All right? So if the sign doesn't change, if the sign does not change, we do not get a local min or a local max. And now, what would that look like, right? What would that look like? Well, let's clear some space here and see if we can draw a picture that would help us out with that. So I'm going to go ahead and erase this now. Again, if you haven't gotten all this written down, you can hit pause and write this down. So let's go ahead and take this off. And let's draw the example that goes along with that last statement. Say we have a function that comes down and it goes like this, right? It goes like this. Well, I guess I'm going to have to, let me redraw that so I can make sure that indeed it does have a place where the derivative equals 0. So it's going to come down, it's going to flatten at a point, right? We're going to flatten right here at a point. At that point, our derivative equals 0. But if we take a look at the tangents to this curve on both sides of C, over here, the slope of the tangent line is negative. Over here, the slope of the tangent line is also negative. And so we do not change signs in terms of the slope of the tangent line. In terms of the sign of our derivative, they don't change at C. And if they don't change at C, we have neither a local min nor a local max. Right? That's what the first derivative test is telling us. We don't have a local min and we don't have a local max. So the first derivative test is our secret weapon when it comes to finding local mins and local maxes. That's what the first derivative test does for us. Okay. So if we go back, right, if we go back to the example that we had done just a second ago, if we go back to that example, you still have it in your notes, I still have it in my memory. If we go back to that example, we had something that went like this, right? Our critical numbers were x is 0, x is -1, and x equals 2, right? These were our critical numbers. And what we determined, right, what we determined was when we were smaller than -1, when we were less than -1, we said we were negative. And then here we were positive, here we were negative, and here we were positive. Now, one way I like to think about this when I'm writing the sign test, of course, the whole sign test would be up here. When I'm thinking about this and I have to come to my conclusions, I like to just use my pencil underneath my sign test, and I think to myself, well, this is a negative. That means my function's going down. This is a positive. That means my function has started going up. And then if I look at what I've drawn here, I can see that this is a local minimum. I reverse the game over here, right? Over here, I say, okay, my function's going up on this side of x equals 0, up on this side. But then over here, it starts going down, and then I can see that this is a local max. Now, we can remember what the first derivative test told us, right? We can remember the first derivative test said if it changes from negative to positive, we have a local min. But if we do this little sketch, then if we get a little nervous on an exam, we get a little shaky on our homework, we can look at our picture and go, oh, yeah, that's what it said. I remember that now. So over here, what's happening at 2? What's happening at 2 is we're decreasing on this side, so the graph's going down, but we're increasing on this side, so this is going to be a local min. All right? Now, remember, if they ask us for the local minimum value, then they're not asking us for x equals -1 and x equals 2. We have to pay. You have to pay attention to the question, right? How is the question written? If the question says, where is the local mins, in this case, of f? All right. If that's the question, where? Well, then the answer is very, very clear. The answer is going to be the local minimum is at x equals -1, and the other local minimum is at x equals +2. All right. Now, that question is asking us for the location of the local mins, not the value of the local mins. If it says, what is the value of the local min? Or maybe it says, what are the local minimum values of f? Well, to find those, we have to find f of -1 right? We would have to calculate f of -1. And if we would find f of -1, we would find out that that's equal to 0. Right, that's equal to 0. If you go back and look at your function, right, your function was 3, because I'm plugging in -1, so it'd be 3, then it would be -1 cubed, right, -1 cubed. Well, we can just write the function back down right here real quick if that's going to make it easier for you. So the function was 3x to the 4th minus 4x cubed minus 12x squared plus 5, right? Plus 5. So if we're going to plug -1 in here, what are we going to get? We're going to get 3. Here we're going to get -1 cubed. That's going to be -1 times -4. That's going to be 3 plus 4 is 7. Take away 12. So that's going to give us -5 plus 5. That's where I got the 0 from. Okay. So this is the value of the local minimum. The other one, of course, would be f of 2, right? We'd have to plug in f of 2. Now, I'm going to cheat on f of 2. I've already done this calculation ahead of time. So if I plug in f of 2, I get -27. Right? -27. I won't have to multiply 2. That's way too difficult for a person of my age. So where do we go next, right? Where do we go next? And I know this is going very fast, but of course, you know, with this video format that we're using for the rest of the semester, the good news is you can back up, listen again, read the book, look at another video if you don't like mine, which, you know, I wouldn't feel terribly disappointed if you did that. It'll hurt a lot less if you don't tell me. So, yeah, I think that's a good plan. Let's just not tell me. So where do we go next, right? We've come up with a plan to help us find the local mins and the local maxes. That's our friend, the first derivative test. Well, what other characteristic is there about a graph that we would want to know, right? What is there? It seems like if we could find the mins and we could find the maxes, then we would have all the information we could possibly want. But if you allow me to draw a couple of sketches here, right? If we'll draw a couple of sketches, if we draw a local max, right? A local max. We've been drawing a local max like this. This is how we've been drawing a local max. Just a simple arc. But there's another way to draw a local max. We could have a local max if the function went like this and then went like this. That's a local max. Now, those are two entirely different ways of growing a function, if you want to think about it that way. Over here, the function is increasing on the left, right? The derivative is positive, so the function is increasing on the left. But while it's increasing all the way up to our local max here at C, if you look at those tangent lines, they are getting less and less and less steep as we move closer and closer and closer to C. So this function is increasing at a decreasing rate. I know those are big words mixed together there, but if we think about it, it's increasing, but it's increasing slower and slower and slower. Well, if we look over here, this function is also increasing. That derivative is positive, 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 and that derivative is positive. But this function is increasing in a completely different manner. This function, while it's increasing, its derivatives are positive all the way as we approach C from the right. However, what's different between this function and this function? Well, the function here on the right-hand side, this function, each of these slopes is getting steeper and steeper and steeper. So this function is increasing at an ever steeper rate. So we need a way to describe these two types of behaviors. That's our next topic. How is this behavior here described, and how is this behavior here described? Now, the words we use to describe those behaviors, we would say this curve right here, we would say this is concave down. Concave down. We're going to define these in just a second, but right now we're just developing the idea. Here we would say this curve right here is concave. Yeah, you're right. Concave up. Okay. So our next topic here in section 4.3 is to come to a reasonable conclusion on first what the definition of these two phrases are. We need to write that out. And then from there we need to come up with a way of finding out, determining, is this function really concave up? Is this function really concave down? So let's first write the definitions down, right? So here's our definition. Here's our definition. It says a function is called concave up on I. A function is called concave up on I. Right? I is some interval if f prime is an increasing function on I. Now that's the definition of continuity. We would say a function is called concave up if f prime, the derivative itself, is an increasing function. If we take a look at the graph over here, the derivative is increasing. It's getting steeper and steeper and steeper. The rest of the definition says a function is called concave down on I if f prime is a decreasing function on I. So to be concave down, the derivative, the slope of the tangent lines represented by these red hash marks here, they have to be decreasing. It has to be getting less steep, less steep. So those definitions, right, those definitions are literally just that. They're definitions. But like a lot of definitions in mathematics, they're here and then they go away. Meaning that we need them, we need to understand them, but there's perhaps a better way of looking at this. And so let's take a look at the top definition. A function is concave up on I if f prime is an increasing function on I. If we think this through, if we just analyze and synthesize, man, that's a hard word. If we think this through, what can we say about this? It says the derivative is an increasing function. Now, we've already talked in this lesson about the derivative and what it means for a function to be increasing. We said for a function to be increasing, the derivative has to be positive. But here we're talking about the function's derivative is increasing. So what we're saying here, if we put those two concepts together, is the derivative of the derivative has to be positive. Because if we take the derivative of the derivative and get a positive, then the derivative itself is increasing. And that is a mouthful of words that we are going to simplify really nicely right now. So let me erase this. Now, we're able to rephrase that in a much nicer way in something we call the concavity test. Okay, the concavity test. And here's what we say. We say if f double prime of x, the second derivative, is greater than 0 for all x in I, then the graph of f is concave up on I. Now, that is a lot simpler than saying the derivative has to be increasing, therefore the derivative of the derivative has to be positive. If we think about it, the derivative of the derivative is the second derivative, and so that is in essence what this says. It just says, instead of looking at the first derivative is going to be about local mins and local maxes, we're going to look at the second derivative, and that's going to tell us about concavity. Okay? Now we have it, the second derivative is greater than 0. We're concave up. We can probably guess what's coming now. If the second derivative of x is less than 0 for all x in I, then the graph of f, are you supposed to put spaces between these words? I'm not sure, is concave down on I. Okay, so that's our concavity test. So we're going to use the first derivative to talk about increasing and decreasing. We're going to use the second derivative to talk about concavity. First derivative, increasing and decreasing. Second derivative, concavity. For all you OCD people out there, I'll make sure I get that out of the way before we do this again. All right. Now, there is another test to determine if something is a local min or a local max. It's called the second derivative test. And I'm going to pass on the second derivative test. I'm not going to hold you responsible for the second derivative test. I think the first derivative test is much easier, it's simpler, and it's more straightforward. So we're going to do our problems based on the first derivative test. All right? Now, in terms of material to be covered in section 4.3, that's it. We've covered all the material in section 4.3. So what I'd like to do now is to do a few examples. I'll do a couple of problems from the book and give those to you, and then I will put together an additional video of just problem solving, get that out to you as well. I still owe you a video on section 4.2 where I problem solve, but before I got that video out to you, I wanted to get the video out on section 4.3 in case some of you are trying to get ahead and work ahead. Maybe you're bored already. We were supposed to have class tonight, and it's Wednesday, and we didn't have class. So let me erase this. We'll put a couple of problems down. We'll work through a couple of problems, and we'll wrap up this video. So I'll start with a question like say, for example, number 9. Number 9 says f of x equals x to the 4th. Well, you know, I'm thinking this through. We've already done a problem like number 9 where we had a polynomial. So instead of doing that, let's do, because everybody loves trig so much, right? Trig's everybody's favorite thing to do. Let's do a function where we have some trig. So we have f of x, and we'll see if we can do trig correctly. F of x equals cosine squared of x minus 2 sine x. All right. And our interval here is our closed interval from 0 to 2 pi. That's our interval. So what do the instructions ask? They want to know, where is this increasing and decreasing? Where do we have local mins or local maxes? And where is this concave up and where is this concave down? So it's pretty much the entire experience that we've discussed so far tonight. So, hey, remind me in a second that I haven't given you the definition of an inflection point. So when we get further along in this problem and it becomes time for me to define inflection points, it'd be great if somebody out there would just remind me, hey, Kevin, you haven't told us the inflection point definition. And for all you high school students watching this from my high school class, it's misdemeanor to you. So we've got this function, and we're going to take the derivative. Now, we know going into this, we're going to need the derivative, and we're going to need the second derivative, right? Those are the two things we're going to need. So before we even begin to solve the problem, let's go ahead and calculate both of those derivatives. So what do we get for the derivative here? The derivative here is going to be what? It's going to be 2 cosine x, right? 2 cosine x, because we're bringing down the power. 2 cosine x, we've got to do the chain rule. We've got to take the derivative of cosine. That's going to be minus sine x, right? And now over here, we're going to take the derivative of negative 2 sine x. The derivative of negative 2 sine x is going to be negative 2 cosine x. All right? Now, we're going to factor that. We're going to take out a negative 2. We're going to take out a cosine. What's left? We took the negative out. We took the 2. We took the cosine. So here we have a sine. And over here, we have taken out a negative 2 and a cosine. We have plus 1. Right? Plus 1. So that's our first derivative. And now we're going to need the second derivative, so let's go ahead and do that right here. We'll take the second derivative from this. And if we take the second derivative, we're going to have to use the product rule here to take the second derivative. So what do we get? We're going to get negative 2. The derivative of cosine is negative sine, isn't it? Negative sine x. And then we have sine x plus 1. Remember, this is f prime g. So this is going to be sine x plus 1. Plus, right, plus, now we copy down f, so f is going to be negative 2 cosine x, right, negative 2 cosine x, times the derivative of sine, the derivative of sine being cosine, right, being cosine x. So if we look what we have here, when we look at it in first glance, we don't see anything that we can really factor out, do we? So what we'll do is we'll multiply these together. What are we going to get here? We're going to get 2. This is going to be sine squared x, right? 2 sine squared x. And then that negative times that negative is positive. So we get sine squared times sine. So we get negative times negative. That's positive 2 sine x times 1. So that's going to be plus 2 sine x there, right? Plus 2 sine x. Negative is positive times 1. That's plus 2 sine x. What do we get over here? Over here we get minus 2. Right, minus 2 cosine squared x, cosine squared x. So what are we going to do with this? We're going to want to factor this, right? That's our ultimate goal, is to factor this. And so how are we going to go about factoring this? Well, we're going to use an identity over here on this cosine squared is what we're going to do. We're going to rewrite this as 2 sine squared x, right? Plus 2 sine x, not changing anything there, but this is minus 2. Cosine squared is 1 minus sine squared. Right? Is that correct? Cosine squared is 1 minus sine squared. So since cosine squared is 1 minus sine squared, now we have everything in sines, and that's what we were shooting for here. So negative 2 times negative sine gives us a positive 2 sine squared. We already have a 2 sine squared. That's going to give us a 4 sine squared x. Here we're going to have a plus 2 sine x, right? And finally down here we're going to have minus 2. Now if we simplify that, that's going to be 2 times 2 sine squared x plus sine x minus 1. Right? And we're going to hope that factors. Right? That's our goal here, is to get that to factor. So what are we going to get? We're going to get 2. This is going to be sine x, and this is going to be 2 sine x over here, right? Sine x times 2 sine x is 2 sine squared. Now I need a positive sign in the middle. So if I put a plus 1 here and a minus 1 here, this is going to give me, if I multiply these two together, I'm going to get plus 2 sine x, right? But if I multiply these two together, I'm going to get negative 1 sine x, resulting in the plus 1 sine x, negative 1, negative 1, 1, negative 1. So everything works out perfect here. Now what am I going to do about this? Well, I've used up most of my whiteboard space here taking care of this. So what I'm going to do is I'm going to jot these down over here on the side where you can't see them, but you have them in your notes. And so I'll jot these down over here on the side so we can make use of these. So give me just a second here. I've got f prime of x, turns out to be negative 2 cosine x times sine x plus 1. And f double prime of x turned out to be 2 times sine x plus 1 times 2 sine x minus 1. All right, so I've got those jotted down over here for us. So I'm going to erase this work, get this out of our way, free up some space here. There we go. And now what are we going to do? Well, we're going to try to find the answers to the questions. Part A said, where is the function f increasing or decreasing? So what do we know about increasing and decreasing functions? We know when the derivative is positive, the function is increasing, and when the derivative is negative, the function is decreasing. So we are going to try to run the sign test. We're going to run the sign test. Now, how do we run the sign test? The first thing we need are the critical numbers, right? So using f prime of x, we want to find the critical numbers. Right? That's what we want to do. Now, f prime of x, as you have written in your notes, right? F prime of x turned out to be negative 2 cosine x times sine x plus 1. So what do we have to do? We've got to determine where cosine x equals 0. Well, let me erase here. Let me erase because I'd like to show you a format that I would suggest you use. When looking for critical numbers, I would suggest you start by writing, I'm going to determine where f prime of x equals 0. Right? This is where we're going to do that work right here. So what are we going to do? We're going to look at this. We're going to set it equal to 0. Based on our zero product rule, we have, that means cosine x is going to equal 0, or sine x plus 1 is going to equal 0. Now, if we solve those, right, we need cosine x equaling 0. Now, remember, we're only working in this interval over here, and we have the graph of cosine. Cosine looks like that, between 0 and 2 pi. We'll just jot that down to help us out. And then the graph of sine, right, the graph of sine, we'll jot that down. The graph of sine looks like this. So we need to know when cosine x equals 0. That clearly happens here and here. This is pi, of course. This is 2 pi over here. So when does cosine x equal 0? X equals pi over 2, right? That's one of our critical numbers, or 3 pi over 2. Those are the critical numbers we get from that side. Now over here, we have sine x. This really turns out to be sine x equals negative 1, doesn't it? When does sine equal negative 1? Sine equals negative 1 right here. That's x equals 3 pi over 2. We've already got it. We don't need it twice, but we didn't know we were going to get a repeat there, so we had to check. Now, the other thing we always check, right? That's 2 primes, Kev. That's 1 too many. Wow. Third time's a charm. There it is. So we always check, in addition, when does f prime of x fail to exist? Suddenly I've lost my mind. So it's okay. That's the other thing we want to check. Critical numbers, remember, occur when the derivative equals 0 or when they fail to exist. Because we're working with cosine and sine are continuous. They don't have any place where they fail to exist. There are no holes, jumps, vertical asymptotes. They're defined everywhere between 0 and 2 pi. They're defined everywhere between negative infinity and infinity. So over here, we would just write NA. Right? Now, the reason we like to do that is because we like to write that to let our teacher know, hey, I knew I was supposed to look for that. I did look for it, and it was not applicable. Leaving it blank, it leaves it open to doubt. Did you know you were supposed to find that? And you checked, and you noticed there wasn't any of those points, so you didn't write anything down. We don't want to leave that door open for people to interpret, so it's always best to write NA here if it doesn't apply. All right, so what are our critical numbers? Our critical numbers are pi over 2 and 3 pi over 2. Right? Those are our 2 critical numbers that we have for our function. So we're going to come over here, and we're going to run the sign test now, right? That's what we're going to do. We'll run the sign test. And remember how we run the sign test. And in this problem, I'm glad we picked this problem because this problem has a really interesting little hiccup in it. Well, we write down our critical numbers. One critical number is pi over 2. The other critical number is 3 pi over 2, right? And what was the hiccup I was talking about? Well, if we're not careful, we write our factors down, right? We come over here, we put down cosine x. That's clearly one of our factors. We write down sine x plus 1, right? That's one of our factors. We write that one down. But let's make sure we don't forget this factor. Negative 2 is one of the factors. Now, why is it so important we write down negative 2, you ask? Well, it's very important we write down negative 2 because negative 2 is negative there, and it's negative there, and it's negative there. And if we forget to write that down, then all of our conclusions are going to be reversed because this negative and this negative and this negative would have been forgotten. Now, how are we going to go about plugging in our plus and minuses? Well, we could put in test points. We really could. We could put in test points. We could plug in pi over 4. We could plug in pi. We could plug in 7 pi over 4. We could do that. That's something that's perfectly allowable. It's perfectly acceptable. But an easier way to do this is just to take a look at the graphs we have over here. What do we know about cosine between 0 and pi over 2? Well, cosine between 0 and pi over 2 is right there. It's above the x-axis, so that's clearly positive. What do we know about cosine between pi over 2 and 3 pi over 2? Well, cosine between pi over 2 and 3 pi over 2 is clearly below the x-axis, so that's negative. What do we know about cosine between 3 pi over 2 and 2 pi? Well, it's positive. It's above the x-axis. That was much easier than plugging in test points. Trig is much easier most of the times than a polynomial is, to be honest with you. Now, what about sine x plus 1? Well, if we remember anything from pre-calc, perhaps we can remember that sine x plus 1 is the sine curve moved up 1. If we look back over here, this would be the new y-axis if we shifted, x-axis if we shifted that up 1. Sine x plus 1 is going to be positive here, it's going to be positive here, and it's going to be positive here. We don't have to always just plug test points in. Don't get to the point that, oh, there's a pun. It wasn't a very good pun. It made me hesitate. It was so bad. But don't always think I have to plug in test points. So what do we get here? Plus, plus, minus. This is going to be negative. Minus, plus, minus. This is going to be positive. Plus, plus, minus. This is going to be minus. Now remember, they don't have to alternate. They are in this case, but they don't have to alternate. So what could we say? Remember, we're asked to tell them when is the function increasing and when is the function decreasing. Well, we know it's decreasing here. We know it's decreasing here. We know it's increasing here, right? So this would be decreasing. This would be increasing. This would be decreasing. Now, on top of that, it also said find the local minimum and local maximum values. Now, we have our first derivative test, right? Our first derivative test told us if the function is going down, which it is here, and then it switches and starts going up, function's going down, going up. This point right here, this is a local min, right? Local min. And that's not even on the screen. So we'll move this a little bit. See if we can get that on the screen for you. That's the beautiful thing about whiteboards sitting on countertops. Here we're getting closer. All right. There we go. Now what's going on here? Here we have an increasing function that becomes a decreasing function, so this is a local max. All right. Now, what would we have to do at this point? Well, we could say the local min occurs at x equals pi over 2. The local max occurs at x equals 3 pi over 2. Right? That's where they occur. Now, how would we find them? Well, the local max, right? The local max is f of pi over 2. So if we go back to f of x and we look for f of pi over 2, right? F of pi over 2, what are we going to get? Well, let's bring this back down here so we can see it. F of x is here. F of x is cosine squared minus 2 sine x. Well, cosine squared x is pi over 2. Cosine of pi over 2 is 0, so 0 squared is 0. Sine of pi over 2 is 1, right? Sine of pi over 2 is 1, so this is negative 2 times 1. So our local maximum value here is negative 2. Now, oh, I'm sorry, that's our local minimum value. I got myself a little convoluted there, didn't I? And so let's put minimum here, right? Because this one goes with that one. And now, where would we find our local max? Well, our local max is f of 3 pi over 2. All right? So what are we going to get for that? Well, again, cosine of 3 pi over 2 turns out to be 0, so 0 squared is 0. Sine of 3 pi over 2 turns out to be negative 1. Negative 1 times negative 2 turns out to be positive 2. So we found our local max, we found our local min, we found where we have a local max, we found where we have a local min, we found which intervals are decreasing and which interval in this case is increasing. And so we've taken care of the vast majority of what they've asked us to do. Now, in addition to those questions though, right, in addition to those questions, they also wanted us to discuss concavity. They wanted us to discuss concavity. So let's take this off. If you didn't get all that written down before I started erasing, you know there's this miracle thing. It's this little arrow on your video player, points to the left. You should push that. You can actually back this up. For those of you that backed it up, welcome back to being with us now. We're still erasing. You didn't miss anything. It takes a while to erase. All right, so where do we go from here? We're going to look at the last part of the question. The last part of the question says, what about concavity? Tell us where this is concave up and concave down. Now, we know for concavity that the second derivative is what we need. And our second derivative was 2 times sine x plus 1 times 2 sine x minus 1, right? So we're going to play exactly the same game we just played with first derivative. We're going to go through this. We're going to find the critical numbers. We're going to find out, we're going to run a sign test on those critical numbers. We're going to see where we're concave up or we're concave down. That's how concavity works. It works exactly like increasing and decreasing. So what do we have to do first? We got to find the critical numbers, right? How are we going to do this? We're going to solve two things. We're going to have f double prime of x equals 0. That's going to be sine x, right? Sine x plus 1 equals 0, or 2 sine x minus 1 equals 0, right? And then the other one is, where does the second derivative fail to exist? Look at that. I got it all written down correctly that time. Didn't mess it up. Last time I couldn't even write that. I'm getting smarter. So this turns out in this case to be NA again, right? And well, so much for being smarter. That's what happens when you go out. So this turns out to be NA because, again, these never fail to exist. Sine's continuous everywhere. So we have to solve two simple equations here. We have sine x equals negative 1, right? Sine x equals negative 1. Now, we know sine x equals negative 1. We looked at on our last little calculation, and we got that to be 3 pi over 2. Over here, we get sine x equals positive 1/2, right? Positive 1/2. Now, we need to know when sine equals a half. Well, to find out when sine equals a half, we can do a bunch of things. First of all, we could go back old school on this, right? And we could say, well, which quadrant am I in? What's my reference angle, right? This is the easiest way to do this. Just use your pre-calc. So I want to know when sine equals a half. That's positive. Sine, if we draw ourselves a little picture, right? All students take calculus. Sine is positive here and here. So for quadrant, we'd have quadrant 1, we'd have quadrant 2, which of course we see from here and here in our picture that what sine is positive in quadrant 1. And then we need a reference angle. And sine, of course, is opposite over hypotenuse, right? So we need a triangle with a 1 and a 2. Well, we've got one of those. This is 1, 2, square root of 3. This is our friend the 30, 60, 90 triangle. Sine is opposite, so this is going to be my reference angle. So my reference angle here is going to be pi over 6, right? I need pi over 6 in quadrant 1. I need pi over 6 in quadrant 2. This is 6 pi over 6 because that's pi. So what do we get for our two angles here? We get x equals pi over 6 or x equals 5 pi over 6. All right, so those are our critical numbers for our second derivative. So we're going to run our sign test. So we'll do the same thing we did before. We'll draw this. We have to plot all these points. We get pi over 6, which is here. We get 3 pi over 2 and 5 pi over 6. Of course, 5 pi over 6 comes first, so we get that here. And now over here we get 3 pi over 2. Don't forget we're done at 0 and done at 2 pi. We need to put all our factors here. Now we can put the 2. I made a big deal about the negative 2 last time because it was negative. To be honest with you, when you have a positive constant factor, all it contributes is plus signs. You can leave that out if you want, but I like to remember to put it in. Because if I forget to put this in or get into the habit of not putting this down, then I'm also going to perhaps get into the habit of not putting the negative 2 down, and we all know that that's going to be a catastrophe. So what are our other factors? We have sine x plus 1 here. We did that just a second ago, right? Sine x plus 1. We determined that's positive every place. We can just fill those in with pluses. And then what else do we have, right? We have 2 sine x minus 1. 2 sine x minus 1. So what are we going to do for 2 sine x minus 1? Well, we can pick some test points, right? We can pick some test points and see what's happening there. So what happens? What do we need, down here? If we plug 0 into this, right? If we plug 0 in, sine of 0 is 0. This would be negative 1, right? So that's going to be negative. We could graph 2 sine x minus 1 if we wanted to, right? If we wanted to do that, let's do a little pre-calc. Pre-calc's fun. So if we wanted to graph 2 sine x minus 1, there's no change to the period here. The period's still going to be 2 pi because it's 1x. So we're going to graph 2 sine x. Now what is that going to do? Well, sine's going to look like this, right? Sine's going to look like that. And what does that mean? Well, it just means the amplitude becomes 2, right? The amplitude becomes 2. And so that's positive 2, that's negative 2. This is still pi here, right? And now what happens if we put a minus 1? It shifts this graph what? It shifts this graph down 1, doesn't it? It shifts this graph down 1. So what do we know? Well, if that graph shifts down 1, then the new y-axis is going to be, the new x-axis is going to be right here, right? That's where it's going to be. Now, we already know when that equals 0. We found these points. We know this point right here is pi over 6, and we know this point right here is 5 pi over 6. So we can do our sign test off of this graph if we wanted to. We could say, well, this is pi over 6. This is 5 pi over 6, right? And so we know we're negative here, we're positive in here, we're above. Remember now, this is our new x-axis once we shifted the graph down 1. So we're positive here. Now, what about from 5 pi over 6 to 3 pi over 2? Well, 3 pi over 2 is here. So we're negative there, and we're negative here. So what does this give us as a conclusion? Well, let's see what we decide. That's positive, positive, negative. That becomes negative. That's positive, positive, positive. That's positive. That's positive, positive, negative. That's negative. That's positive, positive, negative. That's negative. So here we're concave down. Here we're concave up. Here we're concave down. And here we're concave down. If you wonder what I'm waiting for the fact that I asked one of you to remind me that when we got to this point, I was supposed to tell you about inflection points, and not one of you said a thing. At least not one of you said anything that I heard. So here's what we need to know. When concavity changes, this point, because there's a change in concavity, we call this point an inflection point. That's called an inflection point. Here, concavity up, concave down, also an inflection point. This, however, right, this is not an inflection point. Not an inflection point because concavity didn't change. So, when you see in the homework, find the inflection point, specify the inflection point, this is what they want you to do. They want you to tell them, well, it changed from concave down to concave up. Therefore, pi over 6 is an inflection point. It changed from concave up to concave down. Therefore, 5 pi over 6 is an inflection point. It didn't change. The concavity did not change at 3 pi over 2. Therefore, 3 pi over 2 is not an inflection point. Okay, with that, I'm going to close out the lesson on section 4.3. Again, I'm going to prepare another video with some more homework problem solutions on it. Hopefully this one was solved correctly. I didn't check it. And none of you spoke up, so I'm going to just assume it's all right. So I will put this video out there for you, and then I will do a couple of more videos on problem solving in section 4.2 and 4.3. All right, I hope everybody's having a good time. Thanks for playing along.